speaker is Reza Razavian. He is an NSERC postdoc fellow at the Action Lab at Northeastern University, working with Dagmar Sternad. And he's going to talk about human control of complex objects, stochastic optimal control feedback, and beyond.
Thank you. I was looking for that. Okay, thank you for the introduction, Nidhi. My name is Reza Razavian. I'm in the same lab as Marta, and she presented very exotic results on manipulation of whip. I'm going to talk about manipulation of another complex object, and I'm going to give it a bit of a modeling twist. So before I talk about that, I want to mention that we have learned a lot in the previous maybe 2 or 3 decades about properties and features of human motor control system by analyzing and designing experiments in a 2D motion and analyzing point-to-point reachings. For example, we have learned about the temporal aspects of motor adaptation and its relation to error, perceived error, or we learned about the importance of having internal models and optimality principle in guiding these movements. However, this perhaps is a very large simplification of the movements that we interact and produce in our daily activities. For instance, this is perhaps an exaggeration, but in this case, it is no longer visible what is the error signal that drives human motor adaptation, for example. Or when we are dealing with these extremely complex situations, how much information is available and what is the internal model representing here? Or what is the objective that the humans are trying to optimize in a context of an optimal feedback control? So motivated by all this, our research group has, in the past few years, have moved into analyzing complex objects and how humans deal with these situations. And our previous work has shown, for example, that when there are complex underactuated dynamics, people, for example, choose predictability over their effort, or they seek stability of the object, and they actively try to reduce the transient behaviors in these interactions. And Marta just presented that learning, for instance, in manipulating a whip, the subject could improve performance in one style, but they couldn't in another style. So this has been the motivation for our research group to come up with new experimental paradigms. And one of them is inspired by carrying a cup of coffee, where the liquid inside this cup can create first an underactuated behavior, and the interaction of this liquid with the cup creates a lot of not unintuitive, but complex and potentially chaotic interactions that the subjects had to think about and potentially correct for or compensate for. To make things scientifically tractable, we have simplified this by still keeping the important nonlinearity and underactuated behavior of the system by replacing the liquid with a ball rolling inside a circular cup. The system is still underactuated that can create potentially chaotic behaviors that subjects need to react to. In the specific version of this cup task, we were asking first of all, the system were simulated in a virtual environment, and the participants were interacting with the simulated cup and ball by moving a haptic robot that would produce forces back on the participant's hand, and they could feel the effects of this ball rolling inside the cup. And the goal of this task, if I can play this, was to carry the cup from the start box to the target box, and they were explicitly instructed, try not to lose the ball, and the ball would roll forward, and if it had reached the rim of the cup, they would lose the ball and the trial would be a failure. We simulated 3 conditions, and subjects performed 3 blocks. In one block, the ball was essentially glued to the cup, and the cup and ball system formed a rigid object. In the second block, the ball was free to roll inside the cup, and this would produce these underactuated interesting dynamics. And the third block, we had another perturbation to excite the system even more, and the subjects had to kind of find a new strategy and preempt for this perturbation in order to keep the ball and finish the task. So I'm just going to first show you how the subjects performed in doing that. As expected, when the ball was fixed and the object was behaving as a rigid object, they were showing this bell-shaped velocity profile that was smooth, and this is what we would expect from manipulating a rigid object. Things get interesting when there is this underactuated effects of the ball, and clearly the subjects no longer follow the smooth bell-shaped velocity profile, and their interaction forces also change accordingly. And the last interesting behavior that we see in the subject's data is the way they react to this perturbation that is visible in both their velocity profile and the interaction forces. Then the important question is, what processes are in place or can give rise to the behaviors that we observe? And to answer this, we took a modeling approach. There are a lot of questions to answer here. For instance, what is the objective that the subjects care about? Does the stability of this underactuated system matters? What is the effect of the body and the object interaction dynamics? And perhaps what is the role of sensor information coming into the system? To answer a few of those questions, we referred back to the existing hypotheses in the motor control literature. One of the earliest models in this regard is a minimum jerk model that puts a lot of emphasis on the execution, planning, and perhaps execution in kinematic space. And it postulates that the movements are planned as a maximally smooth trajectory. Another class of models is dynamic primitives. And this model puts a lot of emphasis on the dynamic side and postulates that the movements are generated as the evolution of a dynamic system that drives the body and the interaction with the environment toward the target. And one important component of this dynamic primitive model is mechanical impedance, essentially a spring and damper that is being driven as if by moving its free end and moving it in through a space. And that zero force or reference trajectory of this spring damper system is postulated to created by an attractor dynamics that produces a stable motion through time. But often this has been replaced in the existing models with the same minimum jerk profile for a discrete motion. Lastly, an important model in the motor control literature is postulating that there is no pre-planned trajectory in place, and the movements are essentially being produced through a fine-tuned feedback gates that act based on sensory information that drive the system to the target. So what I'm going to show you next is tailoring these models as a generative model that can predict behavior in manipulating the cup and ball. As expected, all of these models have been shown to be successful in explaining or recreating behavior when the object is simple, a rigid object. All of them are virtually indistinguishable in their prediction of a smooth bell-shaped velocity profile and the interaction forces. Things get interesting when there is this underactuated effect of the ball rolling inside the cup. The pure minimum jerk model is obviously unaffected by the ball and continues to predict a bell-shaped profile, whereas also including an impedance operator does not change this prediction much. But the optimal controller that knows the dynamics of this ball predicts something qualitatively different, and I want to point your attention to this region of the velocity profile. And this effort minimizing controller predicts that the ball, as the ball rolls forward, it produces a resistive force on the cup that decelerates it, and this controller does not oppose that in order to minimize effort. So some of the important messages here is that the object dynamics is critical and its knowledge is important. And another thing is that effort minimizing controller does not replicate the behavior well in this scenario. Another interesting behavior happens when there is perturbation. And I want to contrast the prediction of these two models, the optimal feedback control and the one with an impedance operator. And as you can see, the optimal controller shows very stiff behavior, characterized by a small change in velocity and large transfer of the perturbation force to the hand. Whereas the impedance, the model with an impedance shows much more smooth and compliant behavior as observed in human data. And again, the messages here is that mechanical impedance seems to be an indispensable component in interaction with dynamic objects. And the feedback loops through sensory information is not enough to capture that. So the way to try to create a model that can combine all these messages. On one hand, we have the information that the mechanical impedance is critical in interaction with the environment and dynamical objects. And on the other hand, we need to have a mechanism that produces the reference point or zero force trajectory of these spring damper systems, knowing the dynamics of the arm and the object. And the solution we came up with was to take these dynamic primitive framework and embed, instead of having a pre-planned trajectory for the zero force trajectory, we use an optimal controller to generate these attractor trajectories on the fly without any pre-planned motion, using a fine-tuned feedback gain that acts based on sensor information. And now here we are faced with an option. So either to minimize the jerk or maximize the smoothness of this trajectory, or minimize the effort in driving this trajectory. And finally, to the punchline, as you can see here, the effort minimizing model, although it shows much better behavior post perturbation, it still predicts the deceleration in the cup that we do not see in participant data. Whereas the jerk minimizing controller penalizes changes in cup velocity and predicts behavior that is well matched the by the data. And with that, I want to just summarize what we have.
So why don't you pull up your summary slides and you can start, just because we might run out of time, and we can answer the questions. So first of all, that was a great talk. The question is from JJ Urban, and he asks, would your results for the optimal control model not be different with real arm dynamics rather than a point mass?
Um, that is a good question. I haven't tested that, but given, uh, I'm just giving you my guess, given the similarity of the results that is often observed in other motor control studies that compared a point mass to the human data and also arm dynamics with the data, a point mass has been good enough in explaining or replicating the behavior. So I would guess it wouldn't change things a lot, but that's something I haven't tested.
Great. So if attendees have more questions, they can continue putting them in. We'll try to do another short Q&A at the end with all the speakers. But now let's move on to our next speaker. Our next speaker is